Okay, in this video lecture, we're going to be talking about power functions, which are a special type of polynomial function. Our objective, we want to recognize properties of these functions, of these power functions. Just a quick, what do we know? Well, we know what a monomial is. Looks like I've got a little erasing to do there. A monomial is a one-term polynomial. So we're going to be talking about one-term polynomials that are actually power functions. So define power functions here. A monomial function of the form f of x equals a times x to the n, where a is a real number, and of course it cannot be equal to 0, and n is greater than 0, and it's an integer. Okay, we're going to be, I'll get there in just a second, excuse me. So here are some examples of power functions. F of x equals 3x. This is a degree 1 power function. If you'd like, I'll put a 1 right there so you can see it. We don't write it. It's kind of assumed when we don't have it there. Here's a degree 2. F of x equals negative 5x squared. Here's a degree 3 power function, 8x cubed. A degree 4, negative 5x to the 4th. Okay, so we're going to focus on some general properties of power functions, and to do that, we're going to let a equal 1 and just focus on the power of the power function piece and not the coefficient in this video. Okay, so let's begin talking about even degree power functions. We can separate these into two categories: even degree power functions and odd degree power functions. And before we get into this, we're talking about x squared, x to the 4th, x to the 6th, etc. Let's take a look at it on the calculator and in the graph, and let's take a look at the properties of these. So I'm going to turn my calculator on. I'm going to go to y equals. I'm going to do a y1, a y2, and a y3. My first is going to be an x squared. Whoops, if I can make x squared, there we have it. And then I'm going to go down and do an x to the 8th. And then we'll do an x to the 16th. I want to show you, what takes place with these even degree power functions. Now I'm going to press graph, and you'll see in blue is x squared. In red is x to the 8th. And in black, hopefully, there it is x to the 16th. Okay, let's zoom in a little bit. I'm going to change my window to go from x negative 2 to positive 2, and we'll count by ones. And we'll have y go from negative 1 up to 2, and we'll also count by ones. So there's x squared, the blue. There's x to the 8th, the red. And here comes x to the 16th, which is in black. And I want to point a few things out. I'll tell you, let's go back and put a y, and let's put in an x to the 4th, so we can see one more. Okay, x to the 4th. Here it comes. Okay, so what you can see happening with these even power functions is, notice they're all even functions. They all are symmetric with respect to the y-axis. Okay, notice their domain is all real numbers. We can go from negative infinity to infinity. We could adjust the window and you would see that, but it continues to go up and out. The range, however, starts at 0 and goes to positive infinity. There's nothing negative. Again, our coefficient's a 1. Notice they all cross when they all intersect at negative 1, positive 1, at the origin 0, 0, and at the point 1, 1. Okay? And also notice that as we went from x squared to x to the 16th, they flatten out around 0, and then they get steeper. So they not only steepen as they go up, but they then flatten. And if you were to come in here and zoom in on the origin, I'll come in and zoom in right here, you can really see how that takes place, this flattening. Look at that. There's x to the 8th. That's very flat. Here's the 16th coming across. That's flat. A little flatter, actually. It's hard to see it. And here's the 4th. So a lot of flattening taking place in these power functions. I'm going to zoom back out. And we'll come back to where we were. There's x squared. Again, notice it's x to the 8th here, steeper, flatter. X to the 16th, steeper still and flatter still. And then x to the 4th, a little less steep because it's in between x squared and x to the 8th. Okay, so let's note these here. Okay, symmetric are even degree power functions. And again, I'm looking at a coefficient of 1. Okay, they are symmetric with respect to the y-axis. They're even functions. Their domain, the set of all real numbers. In interval notation, the domain goes from negative infinity to positive infinity. The range is the set of non-negative real numbers. The range goes in interval notation from 0 and including 0 up to infinity. The graph always contains the points negative 1, 1, 0, 0, and 1, 1. And finally, the larger values of n, the larger values of the exponent, cause the graph to flatten out near 0 and rise more steeply to either end. Okay? So our even degree power functions. Now let's take a look at our odd degree power functions. And again, with odd degree power functions, x cubed, x to the 5th, x to the 7th, etc. Okay, let's gonna go back to our graph and take a look at what happens. So back to y equals, I'll clear those 4 out, and this time I'll do a better job of putting them in order. X cubed. Okay, let's go to x to the 7th. If I can find the x again, x to the 7th. And then let's go to x to the 11th. I'll skip by 4s, how about that? Maybe we can see it more clearly that way. X to the 15th. Okay, and I'm going to go to the zoom and do the standard window again. Start off there. Here comes x cubed. Here comes x to the 5th. X to the 7th will be black. And then x to the 7th, x to the 11th, and then x to the 13th, 15th, I think I had. Okay, let's go back and check what I was talking about here. 3rd, 7, 11, 15. Okay, let's zoom in. I'll go to my window. Let's again go from -2 to 2. Okay, and the x direction and the y. Let's do the same thing. -2 to 2. Okay, here's x cubed. Here's 7. Here's x to the 11. Okay. And here's x to the 15th. It'll be in, I think, pink. There it comes. And you can see similar things taking place. First off, you're coming in, you're rising, you're going through the origin, and then you're rising again. Okay, so this is symmetrical with respect to the origin. Your odd degree power functions are symmetrical with respect to the origin. Okay, domain, well, all values from -infinity to infinity. Range is the same, all values from -infinity to infinity. Okay, notice this graph. Well, it also crosses, all the graphs also cross through 0, 0, but in this case, while they hit 1, 1 right here, it's -1, -1 down here they all cross through because of the odd nature, the symmetry with respect to the origin. And then the same idea, as the power increases, it not only steepens, okay, it steepens as it rises or falls, it also, like the even powers, it also flattens out around the origin, okay? So the same ideas here, a lot of similar ideas. Okay, odd degree power functions, symmetric with respect to the origin, they're odd functions. The domain, the set of all real numbers, I wrote this in set notation, all x's such that x is a subset of the reals. The range, also the set of all real numbers, all f of x's, or all y's if you prefer, such that f of x is a subset of all the reals of the real number system. The graph always contains the points, -1, -1 in the third quadrant, the origin 0, 0, and 1, 1 in the first quadrant. And again, with larger values of n, larger values of the exponent, the graph flattens out near 0, just as it does with the even degree power functions, and it rises, or in this case falls, more sharply. Again, very similar to the even functions, even degree power functions. Okay, let's look very briefly at transformations and what this means, okay? So we dealt with transformations a little bit previously. Let's take the graph of x to the 5th, an odd degree power function, and let's transform it by negating x to the 5th and then adding 1 to it. What is that? What's the result? Well, the add 1 at the end means we're going to shift x to the 5th up 1, and putting a negative sign in front of x to the 5th means we're going to reflect it about the x-axis. Okay, think back again of our transformation work. Okay, so here's another example. This is a graph of x to the 4th, an even function, which we know will graph as a parabola up. Okay, again, x to the 4th will be a little bit flatter and a little bit steeper than x squared. Okay, so this is the graph of x to the 4th. Well, inside the function, we're going to subtract 1. That shifts it to the right 1. And then we're going to multiply x to the x minus 1 to the 4th by 1/2, which means we're compressing by a factor of 1/2 in the y direction. We're going to compress it in the y direction. So a little bit of look as well at transformations with this thing, starting with our base power functions we have here and on the previous page. Okay, so we'll take a look at that as we work with our polynomials and how we graph them and what we know about them based upon their underlying power function.